Okay, hello again everybody. In this presentation we're going to talk about a type of reaction known as a reduction. As you've noticed from the chapter that we're looking at so far, chapter 13, this is all about alcohols. And so this talk is about one main way to make alcohols, and that's actually from carbonyl groups. Carbonyl groups like this C-double bond O here are present in actually several functional groups, some of which you'll have seen before. This one with a carbonyl group in the middle of a molecule is known as a ketone. This guy over on the right hand side here with the carbonyl on the end of the molecule is an aldehyde. You would have seen these a little bit in organic 1. There are other functional groups that contain the carbonyl group, like for example esters, acids. We'll see those later on. But for right now, we are talking about ways to make alcohols from these carbonyl groups via a process known as reduction. You'll have seen something about reduction before, reduction being addition of hydrogen, oxidation being addition of oxygen, okay? And so because these are reductions, as you can imagine, we're talking about addition of hydrogen. And so you might have the question, well, okay, if this is what's being reduced, what actually is doing the reducing? What's my reducing agent? Well, we actually have two of them here, and I'm just underlining both of them. The first one is called sodium borohydride, and really this is boron with 4 hydrogens around it and a sodium. Just to keep things simple, we can essentially say this is really just a source of nucleophilic hydrogen with a negative charge there. And exactly the same thing for this guy down here, lithium aluminum hydride, or I suppose more correctly it should be lithium aluminium hydride, but I guess that's just me being British. Anyway, so we have two reagents here. Sodium borohydride is much easier to use. It's a weaker reagent. Lithium aluminum hydride, although in some cases we have to use it, it's much more difficult to use. I've used it several times, and there have been times when I wasn't careful enough with it, and it is rather explosive. But they both work in the same way. They both act to add in H- to your carbonyl group. They produce an intermediate which is then protonated by your H3O plus here, your acid. Now notice that this reaction, in fact both of these reactions are shown as two separate steps, step 1 and then step 2. This is an important thing, not just here, but for all of organic chemistry. This is what's called a stepwise reaction. Step 1, step 2. In other words, these are done separately. Step 1 first, let step 1 work, and then step 2 comes in afterwards. You'll often see this in organic chemistry, a multi-step synthesis where you have several distinct separate steps, and this is an example of that. If you want to illustrate separate steps, then separate them with numbers. It doesn't matter whether you put 1 above and 1 below the arrow. I just choose to do that myself. It's a personal choice. But whether you put them both above the arrow, both below the arrow, or 1 above and below, it doesn't matter. What is important is that you separate them with numbers so the reader knows they are separate steps. Okay, so let's look a little bit about how we're going to push some electrons here, okay? We know that we're making alcohols, okay? But let's see if we can figure out exactly how that happens. So I'm going to draw my H- here. And it probably shouldn't be too much of a stretch for you to figure out which part of my ketone the H- reacts with. It's the part that's most electrophilic, which of course is the carbonyl carbon. So we're just going to show these electrons attacking that carbon and pushing those electrons from that pi bond up onto the oxygen. And what that does is it creates an intermediate that you won't have seen before, at least not in very much detail, O- here. This is what's known as an alkoxide. All right. We've added our hydrogen to this carbon. Okay, that didn't come out very well. That's supposed to be bonded to that carbon. And so what happens to that O-? Because we're talking about making an alcohol here. All right, I'm going to draw out what the final product of this is. It's going to be our alcohol down here. So where does that last hydrogen come from? Well, as you can probably imagine, it comes actually from our H3O plus. So I'm just going to draw that out here. Here's our H3O plus, just the hydronium ion, or essentially just protonated water. It's just acid. Okay. So there is our protonated water, or our acid. And our O minus from the alkoxide is just going to grab one of those hydrogens, breaking that bond, kicking the electrons onto the oxygen, and giving you your alcohol. And that is the mechanism for all hydride reactions. They all work in exactly the same way. But notice here what sort of alcohol I've obtained. I started with a ketone, and I ended with a secondary alcohol. This is particularly important. Okay. If we do the same thing with this aldehyde, I'm not going to go through the whole mechanism again because you can see what the product's going to be. Notice the alcohol ends up on the carbon where the carbonyl originally was. And if we draw out the alcohol product here, just following exactly the same rules, you can hopefully see the alcohol that I form. And notice the difference between this alcohol and the one we just formed. We started with an aldehyde in this case, and we made a primary alcohol. So the type of alcohol you make actually depends on what you start with, and that's particularly important. As I said, both of these reactions work well with sodium borohydride. That's really no problem. Lithium aluminum hydride will become useful here in a little bit when we talk about some other functional groups. So let's move on. What about if I have something cyclic like this? Well, it looks like it might be more complicated, but really it's not. The H- attacks the carbonyl carbon, kicks electrons up onto the oxygen, same as it did before. And I'm just going to draw out the product here because I imagine you will be able to figure this out. I put my alcohol where my ketone originally was. All right. And take a look. I've made another secondary alcohol. All right. Now let's go over to this guy. There is one difference here, and that is we have a double bond. Is this going to make things more complicated? Well, you might think it does, but the fact is it doesn't. If you remember from Organic 1, alkenes react as nucleophiles. They send their pi electrons out to attack electrophiles. And what we have here is H-. We have a nucleophile. So what's the likelihood of two nucleophiles reacting with each other? Well, of course, it's 0. So that means your double bonds actually are perfectly safe in the presence of a hydride reagent like this. So what this means is the product that you get is the same sort of product you would have gotten from the other reactions that we did. We get an alcohol where our carbonyl group was, and our double bond stays where it was originally. Notice we had a ketone here, just as we did here. We should get a secondary alcohol, and in fact, we do. All right, let's move on. What if I was to ask you something else, though? What if we had a question not like, what's the product from reduction of this carbonyl compound, but how could I form this alcohol via a reduction reaction? In other words, what carbonyl compound would I start from? Well, it's basically what we talked about, just backwards. You remember we said before, an aldehyde is reduced to give a primary alcohol? Well, we have a primary alcohol here, so that should tell you what sort of carbonyl you should start with that you want to reduce, and of course it's an aldehyde. This exactly is going in reverse to what we did. We started with the aldehyde and said the alcohol goes where the carbonyl originally was. Well, if we want to draw out the carbonyl that makes this aldehyde, we just do what we said, but in reverse. The carbonyl group must be where the alcohol is, where the alcohol ends up. All right? And because my carbonyl is on the end of the carbon chain here, this tells me I have an aldehyde, which is what I should expect based on the fact that this is a primary alcohol. So this is our reduction reaction right here, just using our sodium borohydride and our H3O+, although they aren't shown here. Now take a look at this one. What sort of alcohol do we have here? You can see this one is secondary. And if we think back, okay, ketones are reduced to give secondary alcohols. So therefore, what sort of functional group would I reduce to get to this? And if you said ketone, well, you would be right. So you just draw out the structure again, but this time with a carbonyl where the alcohol was. So I'm going to draw out the benzene ring here, not the benzene, the cyclohexane ring, and say there is the ketone that I would have started with to get to my alcohol, again with a reduction to form that secondary alcohol. Okay. All right. I mentioned before that we were going to be talking about some other functional groups containing carbonyls, and that's where we are at right now. This, you'll have seen this before, this is a carboxylic acid. And these are reduced in essentially exactly the same way. The only real difference is carboxylic acids and esters, we'll talk about here in just a minute, are somewhat less reactive towards reduction than aldehydes and ketones, and what that means is we have to use a stronger reducing agent, and hence why we have lithium aluminum hydride here. Otherwise the mechanism is virtually identical. We have H-. It's a little bit more complex here, and we aren't going to go into the real specifics of it at this point, but the reaction works in essentially exactly the same way. And I just did the same bloody thing again. All right. Okay, let me do this. I'm going to try this one more time. H dot dot minus. Okay, there we go. So these are reduced down to the corresponding alcohol, same as the aldehydes and ketones are. The mechanism we aren't going to worry about quite so much here, but it is essentially the same thing. So what we're going to do here, if we want to draw out the products, is just, well, do what we did before. I'm going to draw out my carbon chain as it was in the starter material, except where my acid was, I'm now going to have an alcohol. And not just any alcohol, notice this is a primary alcohol. So we now have two ways to get to a primary alcohol, from an aldehyde and from a carboxylic acid. Let's move on to these esters here. Esters you won't have seen very much of. Notice the functional group here, the carbonyl with the oxygen next to it and carbon groups either side of it. That's what an ester is. As I said before, esters and carboxylic acids aren't quite as reactive to reduction, so you need the stronger reducing agent. That's why we have that here. So when we have esters and carboxylic acids, we always need lithium aluminum hydride, because sodium borohydride won't do. Notice in every one of these, it's always the two-step reaction. And just like with carboxylic acids, we get the corresponding alcohol here. The only thing that makes esters more complicated is the fact that we have a carbon here as well, and we have to figure out what to do with it. Well, it's actually more simple than it looks. Because if we're going to take this molecule and we're going to put the alcohol in our product where the carbonyl was, in other words, let me draw out what our alcohol product would be. We have our benzene ring here, okay? We draw these on, and that must mean then that our alcohol goes here. This is a molecule known as benzyl alcohol. Notice this is primary as well. And then that begs the question of, well, what happens to this? Well, actually that is just broken off and made into another alcohol product containing the number of carbons that were in this group originally. All right, so essentially from reduction of esters you actually get two products. So let's do the same thing down here. We have our two separate parts. We have this one, okay, and we have this one. We're going to do the one with the carbonyl first. That's kind of the more important one. So we just draw out our product. We know where the alcohol is going to be. It's actually going to be right here. We know we're going to break off the second part. Now our other alcohol in this case has two carbons on it, because I don't want to write out CH3, CH2OH. I'm just going to do this. And those are our products from reduction. So what we've seen here is a little bit of a summary. Hydride reductions of esters, hydride reductions of carboxylic acids, and in both of those cases we have had to use lithium aluminum hydride. And we've also seen how to make primary and secondary alcohols from aldehydes and ketones. We've also seen how to reduce ketones, how to predict the products, how to reduce aldehydes, how to predict the products. And if we just go back to one thing here, If we just revisit this question, the question originally was, how can we make this alcohol? And what we first said, well, we can make it from this aldehyde. But now we've just seen in our previous couple of slides 2 more ways to make primary alcohols. From esters and from carboxylic acids. So what that means is to make a primary alcohol via a reduction, you can actually make it from 3 different functional groups. For this guy, because this alcohol is not on the end of a molecule, that is much more limiting, and so we can only make this alcohol from a ketone. That's a little bit more simple case. Alright, that in a nutshell is hydride reductions. Okay? Bye for now. We'll see you later.